Poisson probability distribution. In Poisson probability distribution, again, we are counting the number of successes like we've done in binomial and hypergeometric. In binomial and hypergeometric, the number of successes out of the n amount of trials, right? That's what we've done. So 10 coin flippings, and then we count how many times that I tossed heads. So out of those 10. So the possibilities can be 0 to 0 up to 10 for that variable. So that's how binomial and Poisson variables were defined. Binomial and hypergeometric variables were defined. In Poisson setting, again, we are counting the number of times something happened, not out of n trials, but within a specified interval. So that's the difference of the Poisson distribution. So by interval, the interval can be any time period from 9 to 10, an hour. It can be the distance, can be the volume. Okay, so counting the number of successes for a particular interval. So that's the idea of a Poisson variable. So if you think about number of errors per page, so you are publishing this new book and you want to study about what are the chances of making spelling mistakes. So you want to figure out the probability distribution of your variable, which is number of errors per page, right? So that's a Poisson variable because you're counting the errors. So errors, in this case, errors are your success. So counting the successes per page. And then another example can be number of customers waiting in a line from, let's say, 9 a.m. to 10 a.m. So let's say that a superstore, a supermarket is interested in knowing whether they need to open all the checkouts during this time on a weekday. So they want to know how many customers would be waiting. They want to count the number of customers that would be waiting in a line to get the checkout done, get the service, and they want to know the chances, right? What's the chance that 10 people would be waiting in a line from 9 to 10 a.m.? So that might be their question. So this is a Poisson variable. So you can build the Poisson distribution around this variable. So those are a couple of examples, and then in order to build the probability distribution, you just need one information. It's on average. On average, what would you expect? What would you see? So basically, mean. That's what you need. Average number of successes in a particular interval. And some people refer to this as rate of occurrence. So like I said, in binomial case, sometimes these values should be obtained from historical data, right? So a study that has been done previously on the same settings, or a study that can be similar to what you are trying to do. So you can observe the rate from a different study which seems similar to your case. For example, if this is about figuring out the supermarket needs to be having all checkouts open from 9 to 10, so they can look into some other supermarkets that has done this study before, and then get their average number of people waiting from 9 to 10 for their place. So then they can use that as a starting point and then build the probability distribution for their case. Okay, so when you have that piece of information, it's very simple. You just go into Megastat and you apply the rate. So Poisson, it's just all you need is mean rate of occurrence. And here it says maximum x value. The thing about Poisson is that you don't really have an end to this probability table. For binomial hypergeometric, you have n amount of trials. So the table does not go beyond that amount. So if you flip a coin for 10 times and counting the number of heads, the number of heads can be 0 to 10. It cannot be 11. It cannot be 12, right? It's only from 0 to 10. That's it. But for Poisson, there's no end. If you're counting how many customers waiting in a line from 9 to 10, it can be 0, it can be 10, it can be 20, it can be 50. We don't really have an endpoint to the possible values of a Poisson variable. So in order for Excel to stop calculating, or according to your question, you can provide a maximum point. So then Excel will only give you the table up to that point, that possible value. And you have the option to leave it blank. That's what I would suggest, leaving it blank. Then what happens is that Excel is going to calculate the probabilities until it sees the chance of occurrence being 0. So because after chance of occurrence being 0, there's no point of thinking about more and more possible values, right? The chance is 0. So then it's going to decide its own ending point. So that's how Megastat would work in this scenario. Okay, so let's look into a practice question. So in this question it says automobiles frequently arrive at Bronte exit of the Queen Elizabeth Way at the rate of 2 per minute. So that's the rate of occurrence. That's the information they already know from a previous study. Okay, so the rate of occurrence of automobiles arriving this exit is 2 automobiles per minute. And the distribution arrivals approximates a Poisson distribution. And the two questions that they want to figure out is what's the probability that no automobile would arrive in a particular minute. So if we take any minute during the day, what is the chance that no automobiles will be arriving this exit? And then if you take any minute during the day, what is the chance that at least one automobile would arrive at this particular exit? So all you need is this information to the rate. So you feed that over here. And I'm not going to complete this. So let's have a look at the complete probability distribution. Okay, so you can see it starts from 0, it went up to 14, and then after that it stopped, right? So that means, see, you can see once you see 0 probability, so that means there's no chance that 12 automobiles would arrive this exit during the day at any particular minute. Okay, and no 13, no 14, so there's no point of thinking about any further, right? So, so these are the possible values, and like I said, it can go beyond 14 for sure, but there's no point of looking at it because the chance of occurrence is obviously 0. Okay, so now if you look into the questions again, it says, what is the probability that no automobile arrives? That means you simply read this number. So no automobile means number of automobiles is 0. So this is the probability, 13%, 13.53%. And then it's asking what is the probability that at least one. So the idea of at least one is that one or more, right? At least one means it can be one automobile or more than one. So this is a cumulative probability. So this is one or more. So one thing you can do is you can just add all these together. At least one. You can read the summation down here. When you select an array of numbers in Excel, it gives you some of the summaries down here. So the summation is 0.86466. So that's the probability that at least one automobile would reach this, arrive this exit at a particular minute. Or else you can use the complement rule. You know the probability of 0 is this much. So you can do 1 minus that. 0.13534, which gives you the exact same answer. Okay, right. So that's how you work with Poisson probability distribution.